So the zero copy actually comes, this passion I have for zero copy comes because I was working in file systems, and it's really about having a zero copy cache for a file system. So bypassing the kernel. So again, that's a bit insane, because why would you want to bypass such evaluated piece of software? What do you know better than the operating system, right? So for file system, that's actually pretty obvious. The file system is between you and the disk, and in the case of a database, well, you don't really need the file system if you have a pretty good idea of the data structure you have. Let's say, so in our case, we use a technology coming from a company named Levyx, which is neither LSM nor a B tree. But let's say if you have a B tree and you want to write it directly to disk, that's more efficient than going through files. And the other advantage of bypassing the file system is you don't have any surprise in terms of caching, write cache, if you want to be sure that the data is actually written to disk, which is a guarantee we have to provide. So in our case, we have a small buffer of 1 page, which...
So you're using Levyx's stuff on raw block device?
Yeah, so the question is, do we use Levyx stuff on raw device? And the answer is yes. We mount directly an NVMe card and write directly to it.
But you're still going through the kernel for block writes?
So yes, the question is, do we still go to the kernel for the block writes? And the answer is yes.
Do you believe that it would be worth saving that kernel interposition by using something like the SPDK?
So the question is, do you think SPDK is interesting? And the answer is maybe yes.
I know the Levyx folks. I'm wondering if I should suggest to them. I assume you probably also.
Well, that's a discussion we can have. For me, every intermediary we can suppress is interesting, but maybe we would be surprised by the numbers, and that maybe it's not worth it because of the device is actually the bottleneck. I don't have the answer. I don't know. For Optane, that's probably interesting. For the NVMe, the fastest NVMe you can get is what? 2 gigabytes per second in write. So yeah.
You can do it.
Yeah. Yeah.
So you still use the file system for metadata, or do you like naming and access control and all that stuff, or do you not use the file system for that as well?
So the question is, do we use a file system at all? And the answer is, when we go through the Levyx layer, the answer is we don't need a file system. There are different ways you can use us. We have a RocksDB persistence layer that you can use, which is going to rely on the file system. The advantage is then you can use RocksDB open source tools if you want and access the data, etc. Or you can use the Levyx persistence layer, in which case you can either mount a device or mount a file as a device. Yeah, the Levyx layer is faster than RocksDB in most cases, and it's not just because they mount the device directly, but it helps. So yeah,
you only have 5 people working on this data system. You've done all these things.
Yes.
Okay.
The answer is yes. When you suppress sleep, you gain a lot of time. So just to be fair, the low-level persistence layer, we didn't write it, right? It's from the Levyx guys. And again, we were, I think, not one wanted to boast. We've been smart about not writing anything that would not make sense. For example, the trap is if you have a big team, you say, well, we're going to write our own logs, we're going to write our own log-free maps, we're going to do that. But if you are resource constrained, that forced us, because we didn't raise money in the first place, so we had nothing, right? And so when you are really constrained and you have a customer who wants a product, then you can be very smart and go very fast.
You said you had 1 kilobyte pages, right? when you go raw to the raw storage device, you're using 1 KB pages?
The question was we have 1 kilobyte pages. No, what I was saying, maybe I was incorrect, is we have a buffer between us and the disk. We are not 100% synchronous because that would be maybe problematic in terms of performance, and the size of the buffer is 1 page.
Okay.
So it's 4 kilobytes. Generally it's up a couple of microseconds of, yeah, it's acceptable. Trade-offs, right. Yeah, so that's one is interesting. If you send a request to a database, whatever request it is, if it's, hey, here's my bunch of points that I want to insert in my time series, what you have to do is to serialize this data and send it to the server, right? And maybe you are running from a Windows XP, it's real life scenario, right? With 32-bit Windows XP writing to a 64-bit Linux. And you can't just dump the memory on the wire and send it and read it. So you have to do what's called serialization. I think you've heard about it. And we spent a lot of time being very efficient about serialization. Like it's really something that showed up when you benchmark the software and you want to see how much time you spend doing requests, and serializing request is actually using a lot of time. So what we did is, let me check the next slide. Oh yeah. So we leveraged C++ template metaprogramming techniques to see if you could decide at compile time the amount of memory you would need to serialize a structure. And I will give you the most simple example. Let's say you want to send a 64-bit integer. You know at compile time exactly the amount of memory you need to send that. It's 8 bytes, right? Assuming you don't do variadic encoding. And by composition, you can compute the size of the structure at compilation. If the structure is not just a bunch of integer, then you can compute at compile time how much the size of the structure. So you can use the stack instead of dynamic memory allocation. And that can really gives a lot of performance, because doing memory allocation is very expensive compared to just moving the stack pointer.
And sorry, you're talking about the client driver, running out of time. You're talking about the client driver, you're compiling it to be hard-coded for your protocol.
Mm-hmm.
Okay.
So I'm talking about the client and also the server. So you want me to go faster?
Yeah.
Yeah.
How much more do you have to go?
Well, it's almost finished.
Okay, perfect. Keep going.
Okay. So that's basically what we've done is, so I'm sorry to punish you with some C++, but basically we have that code that can detect at compilation if you're going to need a memory allocation. If not, we're just going to use a buffer in the stack. Then just to finish, kind of funny stuff is we use, for our distributed transaction, we need highly accurate timestamps. And yeah, that's kind of interesting stuff to know between operating system. So just to be fair to Microsoft, since Windows 8, it's no longer the case. But yeah, you can be surprised that some system calls this cost 20 nanoseconds. So just nothing. This is more expensive because we have to do some math to get the right time. So just to finish, so like I said, we like to say they have 100x dB. Like when we go to a customer, the gains have to be in this area, because otherwise just use PostgreSQL, just use SQL Server, just use Oracle. And what I want to do is 10,000x. And how I have a couple of ideas, but it's a secret. Okay, that's it.
Awesome, thank you.
Thank you.
So we have time for 1 or 2 questions.
Yes?
You talked about putting shared access data blocks into something called a hazard pointer list.
Sorry, yes,
Hazard pointer list.
yeah, we don't use them.
You don't use
No, just give an example.
Yeah, I heard the opposite.
No,
So I had a question.
so about hazard pointer list, the real reason why we don't use them is because of the patent.
Yeah, I don't think they will work.
Yeah, I also don't think, but I'm not willing to bet the company on it.
All right.
One more question? Have you looked at like code generation for queries, like using the LLVM to turn the query into machine code?
So for queries using LLVM, for the moment the queries we have are very simple, very time series related. As we grow, I think we will have to be more and more smarter and smarter about it.
All right, let's thank Edward again.
Thank you.